Okay, what if I told you that time, well, it doesn't actually pass at the same rate for everyone? And what if gravity isn't a force at all, but a curve in the very fabric of reality? These are some of the mind-bending ideas of Albert Einstein. And today, we're going to unravel them using his own brilliant thought experiments to see how he completely rewrote the rule book for the entire universe.
So, let's start with a really big one. Is time the same for everyone? I mean, does a second for me tick by in the exact same way as a second for you, no matter where we are or what we're doing? You'd think so, right? For centuries, physics confidently said, of course. But Einstein? Well, he was about to show that this simple, everyday assumption wasn't just wrong. It was completely wrong. So to get this, we've got to go back to the turn of the 20th century. Physics at the time, it kind of rested on these two massive pillars. You had Newton's classic laws of motion on one side, and on the other, the new, super exciting laws of electromagnetism. The problem? They just didn't agree. They contradicted each other on one absolutely crucial point. And this wasn't some tiny little error. This was a deep, fundamental conflict that threatened to bring the whole house of physics crashing down.
Okay, so here's the old rule. It's called Galilean relativity, but honestly, it's just common sense. Think about it. If you're on a train that's moving at, say, 100 kilometers an hour, and you walk forward inside that train at 5 kilometers an hour, well, someone standing on the ground sees you moving at 105. Simple, right? Velocities just add up. It's logical. And for hundreds of years, we thought this rule applied to absolutely everything.
But then, a clue came along that just shattered that old rule. The laws of electromagnetism predicted something really, really strange, and experiments proved it. It turns out the speed of light in a vacuum, this number we call c, is absolute. It's always the same. It doesn't matter if you're standing still, or flying in a rocket, or even running towards the beam of light. No matter what you do, you will always measure its speed to be exactly c. It never changes.
And right there, that's the crisis. Let's go back to that train. According to the old rules, if you shine a flashlight from that moving train, its light should travel at the speed of light plus the speed of the train, right? But this new rule says, nope, the light from that flashlight travels at c, always. So which one is it? It seems like one of them has to be wrong. Or maybe not. This is where Einstein comes in with a totally radical third option.
This was Einstein's genius. His breakthrough was to say, what if they're both right? What if the speed of light is constant for everyone, and the laws of physics are the same for everyone? He argued that the problem wasn't with the laws of physics. The problem was with us. The things that had to break were our fundamental, deeply held beliefs about space and time themselves.
And to prove his point, he used his favorite tool, the thought experiment. So I want you to imagine this with me. Picture a long, straight railway track. Now imagine two lightning bolts strike the track at the exact same instant, one way down at a spot we'll call point A, and the other way down at point B.
Okay, so first, let's say you're just standing there, right on the ground, exactly halfway between A and B. The light from those two flashes has to travel the same distance to reach your eyes. So what do you see? You see them at the exact same time. For you, standing still, those two events were perfectly simultaneous. Make sense?
But what if you're on a super fast train? And just as those two bolts of lightning strike, you happen to be passing that exact same midpoint. Now think about it from your perspective on the train. You're actually moving towards the flash of light coming from B, and you're moving away from the light coming from A. So what happens? The light from B gets to first. For you on that moving train, the events were not simultaneous at all.
So who's right? The person on the ground or you on the train? And here's Einstein's absolutely revolutionary answer. You're both right. The very idea of two things happening at the same time, simultaneity, is relative. It depends on how you're moving. There's no master clock for the universe. Time, it turns out, is personal. And once you accept that, this whole cascade of bizarre but totally logical consequences just tumbles out. See, to keep the speed of light the same for everyone, something else has to give. And that something is space and time. They have to become flexible. The faster you move, the slower your clock ticks for someone watching you. The faster you move, the more you get squished in your direction of travel. And it all leads to an ultimate speed limit for the universe. Nothing with mass can ever reach the speed of light. It would take an infinite amount of energy.
But, believe it or not, Einstein wasn't even close to done. You see, this whole thing, his special theory of relativity, it worked perfectly for things moving at a constant speed.
But what about when you speed up or slow down? What about acceleration? And what about the most famous acceleration we all experience every single day, the pull of gravity? This new puzzle sent him on a 10-year quest for an even bigger, more general theory, one that would completely redefine gravity.
And he started, of course, with another brilliant thought experiment. Okay, imagine this. You're inside a sealed box, a chest, just floating in the emptiness of deep space. You're totally weightless. Then, all of a sudden, a rope starts pulling your box up with a constant acceleration. What do you feel? Well, your feet get pressed to the floor. If you drop a ball, it falls, right? So here's the question. How would you know if you were being accelerated through space or if your box was just sitting still on the surface of a planet in its gravitational field? The amazing, startling answer is, you can't. There's no experiment you could do inside that box to tell the difference.
And this led Einstein to a huge realization. A body's inertia, how much it resists being pushed around, and its gravitational mass, how much it feels gravity, weren't just coincidentally equal. He realized they were the exact same property of matter. This idea, called the equivalence principle, was the absolute key to unlocking the whole mystery of gravity.
So if gravity and acceleration are indistinguishable, that led him to an even crazier leap. Gravity isn't some invisible force pulling things together. No. Einstein proposed that mass and energy literally bend and curve the four-dimensional fabric of space-time. Think of it like putting a heavy bowling ball on a trampoline. It creates a dip. Now, if you roll a marble nearby, it doesn't get pulled by the ball, it just follows the curve in the trampoline. That's what planets are doing. They're not being pulled by the sun, they're just following the straightest possible path through space that has been warped by the sun's incredible mass.
I mean, that is an absolutely astonishing claim. But look, in science, a beautiful idea isn't enough. A theory is only as good as the predictions it makes. And general relativity made some very specific, very testable predictions. This was it. The theory would either be proven right and change our picture of the cosmos forever, or it would be torn to shreds.
The first big test was actually a really old puzzle right here in our own solar system. For decades, astronomers knew something was off about Mercury's orbit. It didn't quite follow Newton's laws. Its orbit was wobbling, just a tiny bit, by only 43 arcseconds per century. To put that in perspective, that is a ridiculously small fraction of a degree. Nobody could explain it. Then came Einstein. When his equations for curved spacetime were used to calculate Mercury's orbit, they predicted that exact wobble, down to the decimal. It was a perfect, stunning match.
But the second proof, that was the one that made him a global superstar. It happened in 1919. The theory predicted that something as massive as our sun should bend the path of starlight passing by it. And it predicted the exact amount of bending, just 1.7 arcseconds. So an expedition led by Arthur Eddington traveled to watch a total solar eclipse. As the moon blocked the sun, they photographed the stars right next to it. And they saw it. The positions of the stars had shifted. The light had been bent by the sun's gravity, by the exact amount Einstein's math said it would be.
But maybe the single most famous consequence of all this new physics wasn't about planets or stars, but about the very nature of stuff, of matter and energy. It comes out of his earlier special theory, and I promise you definitely know this one. So what does this famous little equation actually mean? It means that mass and energy are basically the same thing. They're just two different forms of the same stuff. Mass is just incredibly concentrated energy. And energy, it turns out, actually has mass. It completely rewrote the rulebook, unifying two of the most sacred laws of physics, the conservation of mass and the conservation of energy, into one single, beautiful idea, the conservation of mass energy. And finally, taking it all the way to the grandest scale, Einstein's theory of gravity completely reshaped our picture of the whole universe. It suggested that if you have matter spread out everywhere, then space-time itself could be curved back on itself. It could create a universe that actually has a finite size, but no edge, no boundary. Kind of like the surface of a sphere. You can walk on it forever and never fall off an edge, but it's still a finite area. Our universe could be like that.
So, in the end, Einstein gave us this incredible new picture of the cosmos. It's this beautiful cosmic dance, summed up in a famous phrase: matter tells space-time how to curve, and curved space-time tells matter how to move. And that elegant interplay, it leaves us with the biggest question of all. What is the ultimate shape, the ultimate fate of our universe? And that right there is a question that physicists are still grappling with to this very day.